The self-stabilizing gyro belt. On the left you can see the general concept design, with a blue belt rotating around the human's body. On the right, this is the green belt. The green belt is a ball bearing connected to a gimbal with 2 degrees of freedom. One rotation around the x-axis and an additional rotation around the y-axis. All this is powered by 2 motors. For starters, let's see it in action. To demonstrate the effects of the stabilization force created by the gyro, we're going to do 2 tests. Test 1, start with an oscillation motion, turn on the gyros. Test 2, we're going to apply a falling force to the gyro. The gyro is going to absorb the energy by rotating 90 degrees out of phase. A third test that I'd like to show you that I did not include before is the impulse test. Applying an impulse, you can see this moves very easily. When the gyro is on, it will not move easily. How does it work? Inertia. There's 2 ways to increase inertia, mass and velocity. On the left you can see there's an elephant and a mouse. The elephant has much more inertia. Likewise, you can increase the velocity of this elephant and create even more inertia. However, we are limited by design constraints to a small mass, therefore we must have this mouse running very fast. The very fast running mouse in our case is a bearing. You saw this bearing spinning in the previous videos. It weighs approximately 7.5 pounds and has an OD of 21.5 inches, an ID of 20 inches, and is 3/4 of an inch tall. The bearing spins at 500 to 1,000 RPMs.
My name is Pfeiffer. So for our motor selection, we needed to fulfill different motor specifications. First off, we needed to fulfill a torque output of minimum of 0.7 Newton meters. We also needed an output of 1,000 RPMs from the motor. We ended up going with the 775 brushed DC motor. The reason for this is that it was cost effective. The RPM output for each motor was max 20,000 RPMs, and the max torque output for each motor was 0.2 Newton meters. Since the minimum torque that we needed was 0.7 Newton meters, we bought 4 motors to drive the gyro, adding up to 0.8 Newton meters, which was just above the 0.7 Newton meters.
So hi, my name is Schuyler Mann.
I'm Martinez.
And we'll be going into the purpose of implementing actuators into our gyroscopic self-balancing design. So basically the main purpose is to implement these actuators to actively process the gyroscope to reduce the required RPM and increase the restoring force for balance. So as you can see by the schematic, the precession rate is over the y-axis and the gyro torque, or the person falling, is over the x-axis. So as you can see from this equation, that if we can increase this precession rate by actively processing our gyroscope, we can decrease the amount, the speed that this gyro actually needs to spin at. And then also, if we increase this precession rate, we can increase the gyro torque and then thus increase the stabilization torque to balance the person. So 3 possible methods for actuation is electric linear actuator, a slider crank mechanism, and a pneumatic actuator.
So over winter break, we're going to perform an experiment attaching the MPU 6050 accelerometer to the gyro in order to measure the angular acceleration and angular speed. Using this data, it'll help us determine the force and in return the required torque to spin the gyro. This information will dictate whether we go with the pneumatic, linear electric, or slider crank mechanism for the actuation.
Hello everyone, my name is Terence Costigan, and I'm going to be going over the current progress on the electronic system. So at the moment we are using a 12-volt car battery, as this meets our voltage and our current requirements. In addition, it was free and easy to use, perfect for a prototype. So in that first slide and right here in the middle, you see that we have these 4 breakers. The neutral wires are attached to the breakers from the battery, and this enables us to switch the batteries, or the motors, on and off very easily. In addition, if one of the motors starts to draw more than 15 amps of current, the breaker will trip, and this results in the motor shutting off. Then we can assess what went wrong and turn the rest of the motors off in response to that. In addition, we have this on this right side, we have this one hot wire from the battery coming up and splitting off to each of the motors equally, or I shouldn't say equally, but splitting off to each of the motors in parallel so that the voltage is the same. We also have the Arduino and the accelerometer. We set these up on the central axis. This is a temporary fixture, and now we can detect positional data from the gyroscope based on any input that we put on it. So, data that we got this week, we took a bunch of impulse trials. So on the left, we have one impulse trial that was from when the gyro was turned off. and you can see nice smooth lines showing that the accelerometer is operating nominally. On the right, though, we see that when the gyro is on and we put the same impulse on it, we have large drifts away from the steady state. This means that this gyro, or excuse me, the accelerometer is being disturbed by either electromagnetic or vibrational interference from the gyroscope. So we need to fix that and troubleshoot it in the next coming weeks. Off to Mike with the rest of the next steps.
Future electronic considerations will include pre-actuated decisions such as power management for all 4 gyro motors, the torque requirements limiting the motor driver selection, and the filtering and EMF of both motors and ground plates for any electronic components are all decisions needing to be made prior to our post-actuated decisions, which will also impact our power supply, and driving methods will dictate the control scheme of our controller's code. Linear actuators require motor driver control, whereas electrohydrodynamics will require solenoid control.